All right, welcome everybody. In this video, we are going to take a look at vectors. And if you recall, vectors are things that have both direction and a magnitude and a length. And let's think about how we can calculate the length of a vector. So for example, let's consider the vector v, which I've drawn over here. And v is equal to, we're going 1, 2, 3, 4 units over to the left, and we're going 5 units down. So this vector v actually is a column vector that we can write with first entry -4 and a second entry with -5. And we would like to calculate the length of this vector. So notice here we can form a right triangle where the vector v is the hypotenuse of that right triangle. And one side of this triangle is the absolute value of x1, okay, in this case that would have a length of 4, and the other side would be the absolute value of x2, which would be 5, since distances need to be positive values. And then we can recall from the Pythagorean theorem that if we want to calculate the length of vector v, then that's going to be equal to the square root of this side squared plus that side squared. So we can write that out below. So first of all, we denote the length of a vector by putting double vertical lines. So not quite the absolute value lines, we put a second double line over here. So this means inside of this is a vector v. It's in bold here. I've drawn it with an arrow above it. And we want to calculate the length of a vector v. And so by the Pythagorean theorem, we can see that is going to equal v1 squared, which would be the length of this side squared, plus v2 squared, which would be the length of this side squared. So when we square these values, doesn't matter whether we enter negative or positive values, because once we square them, they're going to be positive. So here we can see that the length of vector v is going to be the square root of -4 squared plus -5 squared. So that gives us the square root of 16 plus 25, which gives us the square root of 41. So here we've found that the length of vector v is equal to the square root of 41. Let's take a look at what happens in 3 dimensions. So let's consider a vector w, which is going 1 unit in the x1 direction, positive x1 direction, 2 units in the positive x2 direction, and then 3 units up in the positive x3 direction. So here's this vector w. And down here is the projection of this point into the plane, the x1, x2 plane. And so here we would need to apply the Pythagorean theorem 2 times. So first I have a rectangle which is formed by these 3 red lines that I've drawn. And this one over here, this angle is a right angle. And therefore this triangle that we have is a right triangle. And we have one side length over here, I'll call v3, which in this case is equal to 3. And then we have another side, which is down here in the x1, x2 plane. And I'll just denote this with the letter A, since we don't know what that value is just yet. But we can find this value A because it is the hypotenuse of this second right triangle that we have that sits in the x1, x2 plane. And so for this right triangle, we know that one side is equal to 1 and the other side is equal to 2. So therefore, the length of this side A that we labeled, which is this side of the triangle, which is also one of the sides of the red triangle, we can calculate that length A by taking the square root, in this case, of v1 squared plus v2 squared, which in this case would give us the square root of 1 squared plus 2 squared, which is equal to the square root of 5. So that tells me the length of side A. And now we can go ahead and try and figure out what the length of side W is by using the Pythagorean theorem again. And so now we can say that the length of vector W is going to equal the square root of one side of its triangle, which is A, plus squared, the other side of that triangle squared, which in this case is V3. And so we're going to square v3. Excuse me, I put v3 to the third power. The 3 is the subscript, and we're going to square that. And that's going to give me the length of this side of the triangle right here. So now if I take a and I square it, squaring this is going to give me v1 squared plus v2 squared. And then I add to it v3 squared. So we can see here, if I'm calculating the magnitude of a three-dimensional vector, we have a very similar formula as what we had for the two-dimensional case, except now we have one additional dimension that we need to consider. So let me summarize this calculation down below, that the magnitude, the length of vector w is going to equal the square root of w1 squared plus w2 squared plus w3 squared. Excuse me, I used v's over here to denote the lengths of each of these sides of vector w, so maybe it would be more accurate if I had used w's over here. But the formula is we're going to take the square root of the sum of the sides squared. So for the case of w, we're going to take the square root of 1 squared plus 2 squared plus 3 squared, and that gives us the square root of 14. So let's summarize these results, and let's extend this in general to vectors that are in Rn. So we say that the length or norm of a vector v, which is in Rn, is going to be a scalar. And again, this is going to be a value which is greater than or equal to 0. We can't have negative lengths. And we find this length by taking each of the entries of the vector, squaring them, adding the sum of the squares, and then taking the square root.